Good afternoon. My name's Troy McCormack, and today I'll be doing my presentation on the pitch discrimination within the afferent division of the peripheral nervous system. So, what is the nervous system? How does it work? What's the difference between the afferent and efferent system? What is what is hearing? What is pitch? How do people discriminate between pitches? How does this relate to music? What does it mean to have an ear for music? And can anyone have an ear for music? These are all questions that we're going to be answering throughout this presentation. So just be aware. So first off, we'll start off with what is the nervous system? The nervous system is a system of nerves in our body that allow us to hear something or feel something or sense something with our eyes, our ears, our mouth, or our nose, and we're able to be involved with the environment and then make determination. So when things are coming in, it's called afferent. Those nerves are at the peripheral nervous system, like our ears, and pitch discrimination occurs in the brain from the afferent nerves. So here we have a nice diagram of the afferent nervous system, and you can see here how you might feel something on your skin, and then it travels along the afferent nerve, and here's the nerve body here, and it keeps going into the spinal cord where it would go to the brain, and in the brain it would say, okay, let's go out and let's go on and let's do the efferent now. So let's do something about it. So let's say this muscle was pulling your hand back from something hot. So that's a general system of how the nervous system works. Now, pitch discrimination is a little different, and it mainly occurs in the brain rather than having an efferent response. So the afferent nerves are pretty much the most portion of what's going on with this particular idea. So here we have a graphic of where pitch discrimination would occur in the brain. As you can see on this GIF here of the brain, it's occurring in the fold here, this portion right there. And so that's right here on it's occurring in what's called the lateral sulcus. It is a deep fold within the brain that ties together the temporal, parietal, and frontal lobes. And mainly everything is occurring right here on the second gray photograph here, a diagram, in the insula. So it's pretty much ties in all of it together. It's happening right here in this little fold, which is outlined there in red. So that's the portion of the brain that is affected by this pitch discrimination, and you can see how it really affects that higher level of thinking that humans have. So can anyone discriminate pitch? And the short answer is yes. Yes, with enough training and thought, it's easy and enjoyable to distinguish pitches in music. Not everybody's a musician. So there's a condition known as amusia, and that occurs that occurs without brain damage, sensory or cognitive deficits, and has been suggested as a lifelong deficit with genetic origin. Now, pitch discrimination and an ear for music are different things. Oftentimes, where our brains are able to distinguish patterns of speech and intonations in our speeches. Like the Chinese, they use a lot of, like the Chinese Mandarin, there's a lot of pitches within that language that discern whether or not it's another word or not. So we all can distinguish pitch, but not everyone is a musician. And really, when I looked up to see how many musicians there were in the United States, there's no really reliable way to measure the size of the musician population, because musicians and those who can more fully understand pitch in that musical element are less likely to be able to be included in a study, because we all have the ability to be musicians. It's just how much are we going to train ourselves to do so. So what is pitch discrimination in a more scientific aspect? How can we measure it? There's been a lot of studies, and I want to focus your attention here on um, this portion A of this figure here, figure 9.2 here. You can see here non-musicians, their pitch discrimination is not very high, but there's these little nodes here which are represented in the violinists. So it looks like violinists, according to this study, have the highest pitch discrimination, which is recognized by this P2 here. And this is all in response to certain data that was given to these violinists. So you can see here there's these are EEG traces, and there's 28 channels that they were tested on, and pianists were a little bit smaller in their pitch discrimination ability than the violinists. You can see here the line is just a little bit less than the violinist there. But you see here this N1 and N1C are very interesting because they are like the P2 after the introduction of the tone here, which I'm circling in blue. The electrode in the brain picked up, this immediate N1, which you can see is down here. So it goes into these portions of the brain, and then it goes directly into the N1C, which you can see it's really in that lateral scolus right here. And then there's higher function that kind of goes here, and I apologize for not being able to see that aspect of it in the P2. So yeah, there's a lot of studies being done on this. It's really interesting to see how these pitch discriminations are perceived in the brain. So there's a greater context to pitch discrimination. Musicians have to be trained in order to hear a certain tone. It's often difficult to distinguish, highs and lows when they're so close together on the spectrum. So what's the context in the effects of this pitch discrimination? And one study showed that the perceived, this study titled Context Effects of Pitch Discrimination showed that the perceived direction of pitch changes between a pair of toes depends on the frequency. And it also depends on the prior history of simulation or behavioral response. So there's a lot of research being done into this, and we can see that our past history is going to allow us to have more discrimination. So our training when it comes to discriminating those tones. So this graph here shows the minimal intensity required for a sound of a particular frequency, shown on the x-axis, to mask the frequency, the test frequency. For example, a masking sound of 750 hertz, which is here, would need to be presented at 35 decibels in order to mask a 100 hertz sound presented at 10 decibels. So you can see here there's frequency selectivity that happens there. So what's going on? How does this relate to our actual brain? And so here we have high frequency sound waves. Here's a little diagram of what's going on when sound enters into our brain. So you have a high pitched sound, which is short wavelengths in the hertz here, and that goes into our cochlea and into the basal region, into the ear after it hits the eardrum. And so the eardrum would be here, and then it goes in, and it's going in, and then it gets into this apical region here, and then all of that would go through the auditory nerve, where the electrical impulses are sent to the brain. So this is how this little seashell is how our ears are able to pick up different pitches. And so low pitch sounds would enter into this cochlea a little different than high pitch sounds. And that's the physical differences that occur inside the ear that allow for pitch discrimination to occur. So here we can see a measurement of hearing, the Mel scale. So under 500 hertz, pitch increases linearly and with frequency. The hertz scale is equal to the Mel scale here. Over 500 hertz, so after that, you can see the pitch is varying logarithmically with frequency. The latter increases at a greater rate than the sensation of the pitch. It is estimated that there are 620 pitch levels, each one representing around 4 mLs, or if they are spread over the basilar membrane, as we saw in the previous diagram, 52 micrometers, roughly the width of 6 human hairs. So it's a very finite thing that is very small and allows for this wavelength to come through. And that's why we can only hear in certain ranges. And we've heard that dogs can hear in other ranges, and that's because of the anatomy of the cochlea there. So what are the physical factors that influence pitch? There are several of them. The first one being the intensity level. The pitch of mid-frequencies does not change with intensity levels. However, lower pitches tend to be lower and higher pitches are higher when the intensity levels increases. Another thing that influences pitch is the sound duration. When a sound is short, it loses its spectral purity. Therefore, the shorter the sound, the lower the pitch. Another thing is diplicusis, which is the interaural pitch difference. That's between both of our ears. Here, you can see I'm wearing a headset here, so I'm able to pick up sounds given from my computer, intraorally. So I'm able to get in stereo. That's kind of where that comes from. And these are really interesting headphones because they actually cancel ambient noise, so I don't have to hear my kids screaming in the background. Another thing is, this intraoral pitch difference describes when a pure tone has a different pitch when it is heard with the left or right ear. Although more pronounced in hearing impaired listeners, it also occurs at a certain degree in normal hearing individuals. This pitch difference is also be estimated around 3%. So it changes a little bit. And masking. When certain components of a sound are masked by another sound, pitch can be altered. So if you ever notice that that's kind of like they call it the people talking in a room type of effect. A lot of voices kind of intermingle with each other, and it's kind of hard to distinguish one from the other. And that is an aspect of masking, which is going to be influencing us on our ability to distinguish those pitches that are coming from us. That's why it can be hard to hear sometimes when there's a crowded room and a lot of people are talking, and it's better to get up close and talk to them up close. And this graph here shows a pretty good representation of what's going on with the different hertzes. Here we have 3,000 hertz, and their decibels versus how long they'll last from the human thing. So you can see 1,200 hertz, it kind of peaks off really quickly, whereas 150 hertz kind of takes a long time to kind of do that. So since we're talking about music and pitch discrimination and how our brains interpret it, I think it's prudent to talk about a concept is called timbre. And being able to distinguish one instrument from another playing the same note is called timbre, and it is derived from the spectral composition of sound. So, you might wonder sometimes how a conductor is able to hear everything going on, with a full orchestra, and they have, the violinist and the cellos, and then they have all these different instruments that are playing, and being able to hear just one little note that's different. Well, that discrimination and that pitch and that concept is called timbre. And we have all these sound waves coming at us, and it's this big spectrum. And being able to do that takes a very trained ear, but it doesn't just take a composer. But if you listen to an orchestra or classical music or any music for that matter, except for maybe mumble rap, you can really hear the timbre, and you can really see the difference in tones and in that pitch. Well, thank you very much for your time and listening to my presentation. Here is a list of the references I've used, and feel free to comment on any questions you might have in the comment section of this video. And thank you so much.